Okay, now it's time to talk about significant figures, the bane of chemistry. These are the things that make students crazy and they never, ever, ever go away. No matter what chemistry class you take or physics class for that matter, significant figures are extremely important. I know what you're thinking. I thought I was supposed to be talking about measurements. Yeah, well, I will. Measurements have two parts, remember? They have both a number and, a unit. Well, the number we talked about so far had to do with scientific notation. Those are going to help us in chemistry because we talk about numbers that are ridiculously small or ginormously huge, and scientific notation helps us with that. The other part of numbers that we need to consider are what's called sig figs or significant figures. And then we'll get back and talk about the units and put them both together. First, let's talk about significant figures. Okay, before we can talk about significant figures, I need to talk a little bit about why we need significant figures. And we need them because there's always some uncertainty in your measurement. And you need to be able to communicate to whomever's reading your lab data what your level of uncertainty is. For example, take a look at this pencil. I know for sure that this pencil is somewhere between 25 centimeters and 26 centimeters. I can even say with a pretty certain level that this pencil is greater than even 25.5 centimeters. But I'm not exactly sure where it falls. I think it might be right about there, somewhere between 25.5 and somewhere between 26. If I reported my number as simply, it's 25 centimeters, then I'm communicating to my reader that I'm certain of this digit. But this is the one that I guessed on, and I wouldn't say that that's accurate because I'm not going to guess in the ones place. I'm going to guess somewhere in the hundredths place. I'm absolutely certain of the ones digit. So in sum, I want to say that this pencil is 25.7 centimeters long. What that communicates to the reader is I was 100% certain on the 25. The 7 digit, that was the one I guessed on. Our significant figures communicate to the reader our level of uncertainty in a measurement. If I took a look at this particular nail and I wanted to communicate to my reader how long the nail was, what is my certain digit here? What numbers am I absolutely certain of in this number? Well, for starters, I am absolutely certain that this pen, or rather this nail, is 2.8 centimeters. 100% sure. And I'm pretty sure that it's, because this is segmented off by the tenths place, or by the hundredths place rather, that 2.85 would be a pretty good guess. But what if the nail wasn't sitting right on the line? Say the nail was sitting right there. How could you communicate to your reader that you are going to guess one more digit? Well, if the nail was out here, I might say that the nail is 2.854 centimeters wrong, which would tell my reader that I am absolutely certain about the 2, the 8, and the 5, but I'm going to guess on that digit. But it's sitting not in between the 5 and the 6, the nail's sitting right on the 5. So how are you going to communicate to your reader that you are still absolutely certain of these 3 digits, but you do have one level of uncertainty? We do that by putting a 0 at the end of our number. So we're going to learn later that trailing zeros after a decimal point matter because they indicate a level of precision. We are certain of these three, and we guessed on the last digit. So there's basically a rule that you could use for this, and the rule is that you're always going to guess one digit past what your measuring device allows. For example, this measuring device measures clearly the ones place, the tens place, and the hundreds place, which is why I circled the 2.85. But the digit past that would be, we've got the ones place, the tenths place, the hundredths place. Definitely we have to guess the thousandths place. If I took a look at this particular graduated cylinder, this first one, I'll call this graduated cylinder A. Well, let's take a look at how this is broken apart. We know that the water is somewhere at least 3. And the ones place is definitely a level of certainty. And let's see, there's 1, 2, 3, 4, 5 steps between the 3 and the 4. So take a moment and see if you can figure out the increments on this graduated cylinder. If you said that this graduated cylinder measures in increments of every 0.2, you would be absolutely correct. So this graduated cylinder measures on this very first line would be 0.2. And then the line above that, let's see, 0.2, then this is 0.4, 0.6, 0.8, and then we get to the 0, 0, where the 4 is. Okay, good. So if we take a look at this, we know for certain that this water at least comes up to the 0.4 line. However, this is where water gets to be very interesting because water tends to be attracted to the glass, and both glass and water have these properties called polar, and so it wants to climb up the polar walls, but the water isn't really as high. This divot or dip is called a meniscus. And you always read the very bottom of a meniscus, not where it climbs up the sides. So if I were to trace this meniscus out in a straight line, you're right. Well, it kind of looks like this would be 3.49. One of the reasons I like this is it tells the reader that my measuring device measures accurately beyond the decimal point. And I gotta guess one more digit. Could you have said 3.5? Well, you could have, but I might have had to mark it wrong, see, because you still have to guesstimate that last digit, which would put me at a 0. You always have certain numbers followed by one uncertain digit. Take a look at this graduated cylinder. We know for sure that this graduated cylinder measures to the ones place. But now we have to guesstimate just one more digit. Yeah, I'd call that 1.5, but if you said 1.4 or 1.6, those would be acceptable answers as well. So we use significant figures to communicate to our readers our level of uncertainty in measurement. Now that you've had some basic instruction on why we need significant figures, and you may or may not agree with me on why we need them. Math thinks we don't need them because they're more focused on math. And these questions about significant figures will solve the question you've had of your math teachers with, how many digits are we supposed to round this number to? There's actually a set of rules that tells you that. But before we can get to that, we have to actually be able to count. So the first rule says all non-zero integers. So any number that is not a 0, always, one of my favorite words in chemistry, always counts as a significant figure. For example, 3,456 has 4 sig figs. 125 would have, 3. And this number would have 6 significant figures. Every digit that is not a 0 counts as significant. Seems easy enough, right? Yeah, sig figs, absolutely easy, right up until you get to, that's right, the dreaded 0. There are 3 different rules governing zeros, and they trip students up all the time, so pay attention. We have 3 classifications of zeros. We have leading zeros, captive zeros, and trailing zeros. So let's start with leading zeros. Leading zeros are the ones that come in front of a number, and you will see these in front of a decimal type number, some number less than 1, and these absolutely never count as significant. They're simply placeholders. But in terms of indicating precision of a number, they don't matter. Precision happens at the end of a number. Remember when we were doing the certain and uncertain digits? Yeah, these numbers out here at the end indicate precision. These numbers, they're simply placeholders. They do not count. So this particular number has 2 sig figs. This one down here would have how many? That's correct. It has 4 sig figs. Captive zeros are probably students' easiest zero to identify. Another word for these type of zeros would be sandwiched zeros. And I've lost my pen. There we go. Sandwiched. These are the zeros that occur between non-zero digits. So if you take a look at the one I tried to scribble out, 1, 6, and 7. Those are all significant. They're non-zero integers. And this 0 is sandwiched between 2 different integers. So we call it significant. And this number has 4 sig figs. If I take a look at this next number, there's a 2 and there's a 3, and the 2 and the 3, all of these non-zero digits are significant. But what about all these zeros sandwiched in the middle? Are they all significant? Yes, they are, and this decimal point makes absolutely no difference whatsoever. If you have a non-zero integer, a bunch of zeros, a decimal point, and more non-zeros, they're sandwiched. It's just a really big sandwich. And all of these digits then count as significant. So this number has 1, 2, 3, 4, 5, 6, 7, 8 sig figs. Lastly, this number. These zeros. Do they count? No. They're called leading zeros, and they don't matter, ever. This one counts. What about that 0? Would it count? Yes, it is sandwiched. And this 0, it is also sandwiched. So we have 1, 2, 3, 4, 5, 6 sig figs. Now, scary thing, I can actually hear what you're thinking. Why do we have to count significant figures again? Well, you have to know how to count them so that when we actually do calculations using significant figures, you will know how many decimal places belong in your answer. Okay, now, trailing zeros. These are the ones that kind of give kids a really hard time because the rule on trailing zeros is the word if. It's got an if right in the middle. So, trailing zeros are significant if there is a decimal point somewhere. It doesn't matter where the decimal point, but if the zeros are at the end of a number following some non-zero number and there's a decimal point, they are significant. So this number has 2 zeros at the end. These zeros trail after a decimal point. Therefore, this number has 4 sig figs. How many would this second problem have? Well, if you guessed 2, you'd be correct. There's no decimal point anywhere. So 150, this digit significant, that one is, but this last 0 is not significant because there is no decimal. But what if I wrote the number as 150 and added a decimal point? Would this last 0 count? It would. It is a trailing 0, and there is a decimal point somewhere in this number. So this has 3 sig figs. Our last problem to look at is this one. Give it a try. How many sig figs do you think are in this number? If you said 8, you'd be absolutely correct, because these zeros are captive, so they count. That one is a trailing 0 that follows a decimal point. On this problem, try to pause the video for a minute. Well, I'm sure you can do that. But pause the video for a moment and see if you can answer these 4 questions on your own by counting the correct number of sig figs. And then restart the video and I'll go through them with you. The first one has 5 sig figs. This 0 is captive, so it counts. This one has 2 sig figs. These 2 zeros do not count. They are trailing, but there's no decimal place anywhere. This one has 7 sig figs. This 0 is trailing, and there's a decimal point. These 3 are trailing. There is also a decimal point. Everything is significant. This one has 6 sig figs. These 2, this is a captive 0. This one's trailing, and there's a decimal point somewhere. Now, some of you probably wondered about these 2. They seem to be trailing after a decimal point. But look at the entire number. On this entire number, these 2 zeros are leading zeros. They never count. That's it for the the basic rules of counting sig figs that handled non-zero numbers, which are always significant, and zeros, which are a pain in the butt. There's a couple more small rules left to cover on sig figs and some more practice, and I'll take care of those in the next video. Up next, more sig fig rules. It's just a couple, don't freak out.